Thank you everyone for coming for this presentation. So today I'll be giving an overview of deep learning and how we can apply them in various industries, what's the workflow like, and how we can use deep learning. So we'll be covering these 4 areas today. But before we go ahead, I would like to do a quick poll just to get an idea of the background of each and every one of you. So before we start, it would be good if you can kindly help me fill up this poll. Give me a minute. Yes. Okay, thank you everyone for filling up the poll. So I'll now go on with this presentation on deep learning. So we'll first start off by giving an overview of how deep learning has been applied in engineering and science. So what exactly is deep learning? It's a subset of machine learning and also a subset of AI. So to give an example of what we can do with deep learning, say we have images of vehicles and we want to classify them. So what deep learning does is it goes through your images, you will do automatic feature extraction, looking at how and what features can be distinguished between the different types of vehicles. This can include your cars, your lorries, your buses, or motorbikes, etc. And eventually giving rise to a so-called score of each of the vehicle types and giving rise to a classification results. And often this accuracy can be better than typical machine algorithms. So deep learning in industries have been widely used in industries across many different domains and applications. So commonly used applications are what we see in autonomous vehicles, or be developing digital twins or compressors, or we can also use them for energy optimization or seismic event detection. It can also be used for defects detection. So that was in industry, and in research it has been widely used. So examples of which includes using it to control robotic arms, to detect disease. So if say we have healthy patients and disease patients, we can identify tumors in the sick patients. We will also use them for detecting or quantifying the disruptive effect of tornadoes, or looking at blood flow in our bodies and identifying regions where blood flow is poorer. So deep learning has been applied in many different areas. So these are some examples where we see MathWorks deep learning has been extensively used. So examples of which is predictive maintenance, computational finance, robotics, imaging, and wireless communications or audio. So some of this, we will get to do some of this in our demo on our workshop in session 5. So what we are looking at are examples of applications of deep learning, engineering, and science. So what exactly is deep learning? Deep learning. So this is a framework of deep learning. So typically we have our input layers, followed by hidden layers, and the output layer. So what happens is in the input layer, we get in the data. So as we've seen in the earlier slide, if we are looking at vehicles, your input layer will be images of vehicles. So in the deep learning process, in the hidden layers, then they start to identify features in these vehicles that can distinguish between them. So you look for features that can identify, say, a car, features that can distinguish, say, motorbikes or buses. So all these feature identifications will be done in the hidden layers. So information will be passed from the input layers to the hidden layers, and then giving rise to the output layer, which will be telling you what the image is. Is it a car or is it a motorbike? So there are several types of deep learning networks, and the most common ones would be CNN, convolutional neural networks. Today is, in fact, the most popular neural networks in deep learning. So we'll go through briefly what are the layers in this CNNs. So namely, we look at three of them: convolutional layer, max pooling layer, and value layer. So these are the layers that form the early layers of the networks. So the first layer we look at is convolutional layer. So what this layer does is looking at the patterns of filters that can help in distinguishing your objects of classification. So say if you're looking at numbers and we want to find out, classify the number 0. So we'll first look at what sort of filters patterns can identify this number 0. So examples of this filter will be the 6 of them shown here. So these filters will work for the number 0 and may or may not work well for the other numbers. So with each of these filters, we will then pass through the whole image. So starting from one corner, and we can then go on to the other corner. So you go through pixel by pixel and giving a score of how well this filter is at each pixel. So this is done for all the filters. So at the end of this process, you get a score of how each filter performs at each pixel. And this score is obtained for all the filters that we have. And if you look at the number 1, we have a different set of filters to help score this number. And what is important to note here is that what we are looking at is not just filters that can score well. Filters that don't score well is also an indication. So filters you develop for the number 0 does not work well for 1. And this is also a form of information telling the network what our image can be or cannot be. So having done the filters and passing through the image, what we get is a very large set of numbers. So as I said, you pass through your filter through each pixel in your image. And for each pixel, you get a score. So you actually get a very huge matrix of scores. So what happens then here is we do a max pooling process. So what this does is a downsampling operation. So imagine we have 16 scores here, 4 quadrants, and we pass through 2 filters. So in this max pooling process, we have reduced the size of your matrix, size of your data, from 16 numbers to 4 numbers. This reduction in size is very useful in machine learning, deep learning process, because often data sets can be huge, algorithms can be complicated, and your whole algorithm can take a long time to run. By applying such process to help reduce your input size, you help speed up the run, and most of the time you may not compromise the prediction accuracy of your model. So another common layer that we have is the value layer. So what this does is a thresholding operations. So for the value, it will return all your negative numbers to 0. There are many different types of value is known as activating functions. There are many such activating functions, all with different thresholding. So this will also help to improve the accuracy of your deep learning process and often used in it. So this forms the core of the deep learning networks. And having done through several layers of these 3 layers, we will end up with a different 3 layers. So the first of which is a fully connected layer. So what this does is after it has gone through all the earlier layers, you will now have a score of each of your prediction. So if you are predicting vehicles, you will give you a score of a car, a motorbike, a bus. So for each of these classes of vehicles, you get a score. But score is unbounded and it may not. And just by looking at number, you may not get any idea of how good or poor the classification is. So this is then followed by the softmax layer, where you turn your scores into probabilities. So with this probability, you get a sense, you get an idea of what is the probability of each type of vehicles. And we can then turn this probability into a classification result, which is the last layer. It will basically tell you what image that vehicle is. So there are many, deep learning has been around for a long time, and many people, research groups have built networks So these networks can be used directly for deep learning so that we do not have to build the network ourselves. We do not have to define the layers ourselves. So it serves as a very good starting point for our training. And if needed, we can always do minor adjustments to these networks. And this process is known as transfer learning. So, but we won't go much into that. So this is just an overview of some of these networks in the literature today, and many of which are available to be used directly in MATLAB, such that you don't have to build this network yourself. So what we looked at just now was CNN, convolutional neural networks. Another commonly well-known neural network framework is what we know as recurrent neural networks. So what this does is your output is feedback into your model. So what happens is your X0 is fed into the model, you get an output H0. And this H0 is fed back into your network along with the next input X1. And this process continues for the different inputs. Okay? But the issue or the limitation of having that approach is as your time steps increases, say I have 100 time steps, by the time you reach the later time steps, earlier time steps will have minimal impact on your network. The information is barely captured by then. So a lot of the information for the earlier time steps may not be applicable to the later time steps. To overcome this, people came up with this variation of recurrent neural network known as the LSTM, long short-term memory network. So what this does is it's basically the same, everything's the same process, but in addition, we have what we call memory state. So this memory state will help to capture information even from the earlier time steps. So you get to preserve your information in the earlier time steps as well as in the later time steps. So this will often improve your classification results, deep learning results, especially when earlier time steps have a big impact on the later time steps. So similarly, there's an overview of LSTM network architecture. So same thing, we've got an input LSTM and we end off with the three similar layers that I have described for CNNs. So LSTM can also be used for classification on regression purpose. So in session 5 in our workshop, we'll go through a bit more details on these deep learning networks, and you will get to do some hands-on practice using that. So what we looked at earlier on was deep learning frameworks, LSTM, recurrent neural networks, and CNN. But deep learning is just a part of a process. And this process is often comes in multiple steps, starting with your data preparation. So before you can even do your deep learning, you will first need to get your data and do data preparation. As the saying goes, garbage in, garbage out. So if you do not prepare your data properly, you feed into your network poor data, your network is not going to work well. So simply cannot be used. The next step, we will then doing proper data preparation, we can then do AI modeling, which is our deep learning models. And if we need, we can then use the models for simulation and testing. And lastly, deploying into various systems and processes. So in the next few slides, we will go through some of these processes in terms of data preparation, simulation, and deployment. So first, we have our raw data. Before even deciding what sort of model to use, we will first need to look at the data. So image data, we typically use it for CNN. So we can think of image data as a two-dimensional data. We've got metrics. Whereas if you have a vector data, which is the signal data or text data, we typically use LSTM. And in some cases, CNN can be used. So at the end of the day, all your data in whatever form, it could be audio, it could be images, they're just numbers. So all your data will be converted to numbers, and images are 2D data metrics, and that's how CNN works. Whereas if you have signal data, which are vectorized, or text data, which can also be vectorized, they are used for LSTM. So MATLAB facilitates this whole process of data preparation. One of which is normal data cleaning, data normalization. All this can be done in MATLAB using apps, which I won't show here, but maybe in session 5, we can take a closer look at it. But having done data cleaning, data normalization, a key part of machine learning, deep learning is you need to label your data. Because you are training your data, you're training a model, you need to tell the model what your data is. And this is done during the training process. Only when this part is done, then can you apply your model to do predictions on data that it has not seen before. So to do this, we often need to label our raw data that we feed into the network. So this labeling of data could be just telling the model what sort of data this is. Is it a healthy data, disease data? Is it a good or is it a bad data? So it can be a very tedious process, especially when you go down to say image or deep learning on image. So imagine if you have a vehicle, you will need to tell the model what are the different parts of the vehicle. The wheels, the doors, the windscreen, the wipers, and everything. Because these are the things that will help to distinguish between the different types of vehicles. As such, you will need to label them. And doing manual labeling on all these images can be very tedious, especially if the data set is huge. So MATLAB has an image labeler process that will help to automate this process. And this will be done in session 2, where we will go through in detail some of these apps. Other such apps will be signal labeler, where you can wave, you have wavelets, and you can use the app to help label your wavelets. So this will also be done in session 2 of this deep learning series. So if our data is in wavelets or any form of data, other than just looking at the data and asking ourselves, what sort of features can we extract from this data? There are built-in functions in MATLAB that can help us to automate the feature extraction. So if we don't have a good idea of what sort of features we need, we can start off by applying these functions into our data. And through that, we can get quite a number of features out without having to do any manual work. So one such feature that we have is known as the continuous wavelet transform. So it can allow us to look at wavelets and identify and quantify various features that can define these wavelets, such as the peaks, the average values, minimum values, standard deviation, or area under the curve. So as I said, these are all vector. If we look at the top parts, so these are all vector data. So we use LSTM for it. But there will be cases where you may want to try explore the option using CNNs, convolutional neural networks. And continuous wavelet transform will also help you to convert these spectrograms into images. So what we have done here is we have converted 1D vector data into a 2D image. And this gives you the option of exploring different deep learning algorithms. You could try for the same data set, you could apply LSTM, and you can also apply CNN, and that allows you to compare different methods and see which method performs better. So As I mentioned earlier, there are a lot of apps available in MATLAB. So one such app is Deep Learning Designer. With that, you basically don't have to define any or build any neural networks yourself. You can straight away plug the different options on your left panel and build all your neural networks. And you can click on them to modify and amend any features that you want. So, as I mentioned earlier, that deep learning has been around for many years and people have built a lot of networks available. So this list of pre-trained networks are available in MATLAB and you can use them directly. So in deep learning and machine learning, there are a lot of additional parameters that you need to tune in your network. And often this tuning process can be very tedious and time consuming. And even worse, that you do not know what to tune. So again, there are apps available in MATLAB, built-in experiment manager app, that allows you to tune all these hyperparameters such that you don't even have to do any manual work. You basically tell the app what are the parameters that you want to tune, and your app will do the tuning yourself. So this will save a lot of time, both in terms of tuning and also figuring out how to go about the tuning. So with all this tuning, different pre-trained networks that you can try, so you can then compare the different network architectures and using the same data and see which one perform better. So there are a lot of custom metrics that you can use. So common ones will be confusion metrics, even the curve of ROC curve, or just prediction accuracy. So all these options are available in MATLAB where you can use them to evaluate your different models and your different algorithms. So as I said earlier on, machine learning, deep learning has been present around for many years. So many people have built algorithms that are developed in various systems. So this may include TensorFlow, PyTorch. So and often you may have different processes done in different systems, different algorithms. So you could have part of your workflow in Python and you want to use deep learning in machine learning. You want to use MATLAB for machine learning or deep learning. So rather than rewriting everything, you have the option of importing and exporting models. So you can import models from PyTorch into MATLAB in your workflow, and you can also export them out. So this saves a lot of time, especially when you need to work between different frameworks, different systems. So the last part that I will talk about today is model deployment. So assuming now that we have built our model, so the next thing that we're going to test could be to further test our model, to evaluate the model and how well it performs. So one such process could be simulation work, and Simulink is available to do that. So you can easily build your whole model, input the whole model into Simulink, and you can do further simulation studies to see how well it performs and to change your parameters, optimize and stuff. So you can in MATLAB, you can also generate codes for different systems, CPU, GPU, FPGA. So again, this saves you the trouble of having to rewrite codes in different programming languages. So options like CPU, GPU, FPGA will also hinge on how complex your model is, how much data set are you handling. So for small data sets, you could be looking at CPUs, but when your data sets are larger, you have the option of doing the GPU. And in cases where you need to amend your algorithm, modify your algorithm with data, FPGA could be the options. So MATLAB allows you to generate codes for this systems and without you having to rewrite any of the codes. Because often when you rewrite codes, a lot of information can be lost, things can be done wrongly. So this saves a lot of time and preserve what you want to do in your model. The other thing that we do is have MATLAB production server. This is very useful for scaling up of operations. So MATLAB production server allows you to draw data from databases. So you can import data from it, you can export data to databases. And a lot of these things, your algorithms can be deployed on the cloud, like AWS or Azure. And you have deep learning containers that all the deep learning functions built into it. This will save a lot of time when you do a deep learning process. So MATLAB production server can be deployed both on-site or on the cloud. So this will allow multiple users who wants to look at the algorithm, who wants to use the algorithm, to use them simultaneously. So in session 3, we'll be looking at cloud processing, how some of your algorithms can be deployed on the cloud. And in session 4, we'll look at deployment options, how you can deploy your models in various systems by generating different codes. Yeah. Okay, so with that, I come to the end of the presentation today. But for those who are joining us in our workshop, and if you are unfamiliar with MATLAB or deep learning, you can access our free online tutorials. So MATLAB online on-ramp, deep learning on-ramp. You can just basically Google this first and you can just try out those tutorials yourself. It's free. And if you have any questions, you can always reach out to us.